So for me, it's a pleasure to introduce the second speaker of this afternoon. Is Tiago Pereira from University of Sao Paulo, and he will speak about heterogeneous coupled maps.
Okay, so it's a pleasure to be here and finally talk again about dynamical systems. The last 2 years I was more or less involved in this COVID modeling, but now back to my main research topic. Okay, so a network of dynamical systems for me is this triple. So I have a graph, a local dynamics, and a coupling function. So here what I'm trying to represent in this picture is the following. So I have a collection of dynamical systems, not a single one. So, and each dynamical system is modeled by its own local dynamics, which here is written in terms of F. Okay? So I have multiple copies of these dynamical systems, and they will fill each other, so interact in a certain sense according to a pre-described rule, which in this case here is denoted by H. And what's important here is that this interaction is pairwise, so it's between two nodes. And finally, to complete this triple, I have a graph says telling who is friends to whom. So given this triple, I want to understand the dynamics. So what's very important for me, I want to consider heterogeneous graphs. And basically heterogeneous is precisely this picture you see here, where you see some of the nodes, they have only a few friends, only a few neighbors. And the red blobs, they have lots of connections. These red nodes, they're called hubs. And whenever you have a hub, we say this graph is heterogeneous. My definition is a bit sloppy now, but there are a few definitions of heterogeneity that I will not discuss. But basically means like...
Sorry, Tiago, one question. So each F has the same configuration space? They are acting on the same space? Or it could be...
In this talk, they will be precise... Yeah, thank you very much, Enrique. So in this talk, they will be precisely the same. So it's like X goes to 2X all the way for all nodes.
Okay.
But in the general case, they have different configuration spaces and so on. Okay, so I will focus now on heterogeneous networks. So in the case of homogeneous networks, for example, if this was like a ZN, this is a classical problem in dynamical systems. So Sinai worked on this problem, Kelly, Verani, and so on. I'll focus now on the heterogeneous case. Just to fix some ideas, so this is precisely to address the question. So I have again, so the local dynamics, this will be X goes to X. So I have two copies of the same dynamical system. Then I will couple them. So a typical case that people study is this coupling type of sign of the difference of states. This type of coupling is called diffusive. So if I have no coupling, I have two copies of the same system. So when I couple them together, I have this dynamical system on a torus now. What's important here for me is that I want to study now the effect of this parameter alpha. So I have a family of dynamical system now. I will change alpha and I see how the dynamics change. Okay, so this is the kind of the goal of this small project. In the typical case, you have like a proper network. So here again, so I have Xi is modeling the state of each node. So F is the local dynamics. So you see here again is the same. And now this coupling is complicated stuff. I mean, not so complicated. This Aij is the adjacency matrix of the graph. So if A is connected to J, then this element is 1, otherwise it's 0. So you have a proper graph. If you set alpha to 0, the typical case where you have chaos, so basically you have full entropy and so on, then we're interested in the case where like you start increasing alpha and then something else happens. This is the typical scenario. So, for example, let me tell you some interesting things that can happen. As you increase alpha, then although you start with X going to 2X, these people have done numerics in the for 20 years now on this problem. So you start with X goes to 2X, then you keep on pumping alpha. Then you see some bifurcations going on the network where, like, for example, the main hub, the red nodes, the most highly connected one, it undergoes to a periodic state. The second largest hub undergoes to fixed point dynamics. And as you keep on going down the connectivity, so less and less friends, you are more and more chaotic. So this was an open problem for a few years. So people saw this, they also saw some other phenomena. They've done some experiments. They saw some kind of very similar dynamics to this in the hippocampus of mice and so on. So this became very, let's say, typical case study that people could not abstract mathematically for a couple of years. I will give you one example again here. So I'll do some real-time simulation for you. So this f is x closer to x, so the Bernoulli shift. And the complete function, yes.
Yes. So the open problem was to find the rigorous mathematical formulation of the numerics that was found, or if I understand correctly.
There were many open problems, but finding a mathematical explanation to this one was open for many years.
Okay. Okay.
To be honest, it's still open. But in any case, so this is the f, and this is the coupling function h. So some kind of take one. Okay, so let me show you possible dynamics that happen to this case. So I will show you a simulation. So this is actually real. So I'll run the simulation now. Can you see my screen? Yeah. So probably this goes wrong. So the first time I try, because this is real life simulation, then things go busted. I'll try to explain what I'm about to do. So first of all, this is coupling alpha is the alpha you saw in the equation. So this alpha is this alpha here. So set to 0, I have a bunch of dynamical systems. They are all uncoupled and they are super chaotic. Then I will, what I do, so, let me see. This is what I told you. Okay, so what I do here now, forget about the colors that you see, but between two pairs of nodes, I have a probability P that I connect the two. So this actually, I'm forming a random graph. So every time I click run, I draw a new random graph from this random graph ensemble. Okay, so that's the idea. So I have here a random graph. So this graph G now is fully random. People call this Erdős-Rényi type because, I mean, it's homogeneous random. So between any pairs of two nodes, I have a probability P to connect them. I'll stop plotting the links, otherwise this becomes a bit blurred. It's complaining about some condition, let me say 0. Okay, so now what you see is the following. I'll explain the color coding now. So I will take this node here, you see, the one, can you see my mouse? The one where my mouse is sitting on? So this will be my reference node. So I'll compare the difference between two states. This will be the matrix in the circle. So I'll paint them blue if the two states, they are the same in the circle. So I project it to the circle. And they will be red if they are antipodal. So this is the largest distance in the circle, right? So now, on top of each node, when you see the color, is the distance in the circle that they have to the reference node. Is it clear? So basically,
I don't understand what the drawing means actually. So is the probability of the state, because there are many states. There
are many states. So what I do, I take two states. Let's say I take the state of this guy here, where you see my mouse. Let's say this one, and I take the state of this orange node here. Okay, so what I do, I project into the circle. I'll have 2 points in the circle, right? Then I'll measure the difference between their states. Let's say one is sitting at 0, the other one is sitting at 0.2. So the distance is 0.2. And I come here, okay, 0.2 is blue, then I paint them blue.
Okay.
Yeah. Okay. So this is just a color coding. So if this is just to say, if it's blue, then you're in the same state as the reference node. If it's red, you antipodal to the reference node. And because, I mean, things here are super chaotic, you should see them swapping colors all around. So, so here, for example, they're changing colors like in a very random way. It's just a Bernoulli shift. So if I increase coupling just a bit, so 0.1, so let's say 0.01, let's try to run this again. Then the system is stochastically stable, nothing changes. You should see the same masses should be seen. But as I keep on increasing coupling, so let's see, the system is fully chaotic, yeah? So let me see.
So the coupling matrix you choose in a random way or something?
Yeah.
Okay.
Let me close this one. This is complaining all the time. Okay, so I can't get this. Let me explain now the following thing. So I have here again the same network we're talking about, same color coding, everything's the same. I will plot again the network. But what's the difference between the previous simulation that I had? In this one, I included 2 hubs. So if you see the 2 center nodes now, they are hubs. They have way more connections than the others. So the outer ring, they are still like this random graph, but the 2 center nodes now, they have more connections than the outer ring. So a node in the outer ring that you see here, it has about 6 connections, and a node in the center has 35 connections. So I can change the number of hubs I plot. Okay, so now I have 4 hubs. And here's the same. So if the coupling is small, then nothing happens. You should see color changing, swapping like crazy again. I will stop plotting the links just for sake of clarity. And I'll explain one thing. So now the state of the hub that you see here in the right is my reference node. So every state is being compared to the reference node, okay? So coupling is very small, the system is very chaotic. If coupling is super, super small, then you have stochastic stability. You can prove that the mesh behave in a continuous manner. So color should swap in a random way. But as I keep on increasing coupling, then I start seeing some kind of strange behavior. I'm not sure, I see some waves. I mean, but I've been staring to this picture quite a bit, so maybe I'm hallucinating a bit. So I see some waves going on. I measure these waves, the waves are really there. If you keep on increasing, so let's hit 0.3, so this is the coupling. Then when I run, then I notice something strange, like these other hubs also blue. Do you also notice? Or it's not blue all the way. Sometimes it twinkles a bit, sometimes it's blue, and then sometimes it's light blue, but it's mostly blue. So this means that this hub synchronized to this other hub. Okay, so let's increase the number of hubs. So now it will be 4 hubs. So here are the 4 hubs. And you keep on running, so eventually they become blue. And you see kind of strange behavior. Sometimes they are blue all the way, and then you have like excursion to reds, then they become blue again, but they're mostly blue. So this means like they're mostly synchronized. This top guy here is slightly stubborn, doesn't want to synchronize, but I can run the simulation again. And this is something I can measure. How long they stay blue, whether they stay blue at all, and so on. So let me plot just 2 hubs because maybe it's easier to see the figure. So we only have to pay attention to 2. So they are blue again. So if I keep increasing the coupling, so 32, let's see what happens. Still blue. But if I push this too hard, let's say I double this, 60, then I lose synchrony. At this time, I can see some, I'm not sure whether you see some waves, like there's some kind of wave traveling to the network now. You can measure these waves and plot on the graph. These waves are really there. Okay, so what people wanted to understand is this kind of thing here. Why the hubs, they would synchronize? What are the dynamics of the hubs now? How do they compare to the network? So does the synchronization time depend on the network realization? So every time I click here, I have a new network. I draw this from this new ensemble. And apparently this is a very robust behavior across networks. So I'll go back to 0.3 again. So we see this guy synchronized. You see, now it's taking quite a while for it to synchronize. Sometimes it's fast, sometimes it's slow. So now it's particularly slow. Okay, so this is the type of dynamics I want to understand, and what's the impact of the network structure on the possible dynamics. So the situation now, yes?
Yes, one question. So first you started with n, how do you say, n hubs, a large number of hubs. Each one is a dynamic on the circle. It's an expanding map on the circle.
Yes.
And then the graph is telling you which is the coordination, whatever, how each variable depends on the other systems.
Yes, precisely.
So basically but at the beginning, if you assume that all are disconnected, so you have a map in the torus, n-dimensional torus, where n is the number of, and it's expanding on each variable.
Yes.
So if you keep connecting, so still you're having a map on an n-dimensional torus.
Yes.
All of them with the same degree, so actually they're finished being homotopic. So you cannot destroy periodic point for homological reasons. So I don't see how do you say that if for certain variable you will converge to periodic points. So this is
this is true. This is I maybe what is said. Let's see what people see. People saw numerically. This was the impression that people had. So whether this is true or not, I don't know. And you're saying this is not true. And I will not claim this is true, by the way. Thank you very much.
So maybe you say what you see, this is an attracting periodic point you can create. It's no problem. So the question is, it's not that everything is going just to become an attracting periodic point. This is what is the meaning exactly of what is claimed over there?
I will make this precise, maybe
okay.
Like 10 slides. But basically it's the following. If you do the simulation plots, you see a periodic 2 orbits, left knob exponent negative. So there is some noise, and I will talk about what the role is. But you're totally correct. Okay, so the first thing you can prove actually is the following, that that if you start with again, so if I start with the Bernoulli family, so X goes into X, so it's expanding map. So with high probability, so what this means when the network becomes very large, so the number of systems is very large, then you can prove there is an open set of coupling functions such that homogeneous random graphs, the first one I showed you, they can globally synchronize, they all converge to the same states. This behavior is very robust, so you can perturb it, you can change F slightly, this behavior will persist. So now it's also easy to prove that heterogeneous network. So when you have hubs, these hubs, the network can never globally synchronize. So this behavior is always unstable in this network. But the hubs, they can synchronize. And the hubs, they can slightly change the dynamics across scales. Across the scales means like depending on how many friends they have. Okay. So the first claim that random homogeneous networks can globally synchronize for you guys is an exercise in normal hyperbolicity. So putting the correct coordinates and the correct things. Basically, I'm saying that all nodes, they have the same state. So it's like an invariant manifold of the problem. And then you calculate normal contractions. If you do it, you run into some problem of spectral analysis of the graph Laplacian, but I guess, okay, this is like standard analysis. The dynamics of the hubs is slightly more complicated. So let's discuss, because the dynamics of the hubs now will become a global problem. So the first thing to notice is that the hubs, they actually interact quite strongly to the other nodes. So it's very hard to try to cook some kind of implicit function theorem to make things work. There's another pain here in this problem, is like if you see all the tools that Kela Liverani used for the project, like if you have a homogeneous graph, let's say Z2, then what they use heavily is the diameter of the graph. This means like the largest distance between any two nodes is basically proportional to n. But here, because you have the hubs, the diameter of the network is proportional to log n. And actually, depending on how you cook, it's proportional to log n. So this basically, I mean, what's the idea here? If I want to connect any two nodes, I hop to the hub, hop to the other hub, and hop to the node. So in a few steps, you are able. So this problem seems like super complicated, but actually has some kind of trivial flavor. Let me try to convince that this problem is not so tough. Because actually, what's the key idea here? The key idea is that interaction is kind of, for the low degree nodes, is small, but for the hubs is kind of large. So if I could prove that actually the chaos is kept in these low degree nodes, then I could pretend these low degree nodes, they're kind of random variables. So then I could actually replace this big summation that I have here with the neighbors with some kind of, center limit theorem. So I can write equations for the mean and for the fluctuations. And actually, if you do this, if you forget mathematics or forget any proof, and you just plug these ansatz and solve this problem by self-consistency, you can find equations for the mean, equations for the fluctuations, you get very far to this problem. What is maybe for you guys is not surprising, for me was surprising, is that actually these nodes, they're not independent. And so I was talking a few years ago with Sebastian Hunstein, so we are able to cook up an example where like correlation is always good in the system, so it's unavoidable. And this has to do with visits to Bedsets of the phase space where the system potential is not hyperbolic. So although you start with hyperbolic system, once you couple maybe hyperbolic systems.
But Tiago, you
yes.
you have a coupling of 2x mod 1 maps on this.
Yes. Yes.
I'm completely confused. What means synchronization?
Synchronization means.
I think I was lost earlier.
Let's take the case where I have only two. You're super correct because I did not define synchronization. So now I just noticed that was silly. Synchronization means like x equals to y all the way through. And if you look at this equation, if you plug x equals to y, this is invariant manifold of this.
But they move chaotically.
Yeah, they move in
but at the same way.
Yeah.
I'm sorry, Tiago, what do you mean by visiting bad sets? Because what is a bad set in a uniformly expanding context?
I will explain this.
Okay, thank you.
Yeah.
Sorry for the.
I have this thing. I say something which I didn't fully explain. Okay, synchronization means like all the states that are precisely the same. Which for this coupling here is, I have this invariant manifold of the problem.
I'm sorry, Tiago, excuse me again. And when you have synchronization, you have some rate of synchronization, or this is too much?
Say again. I did not.
No, you have that the orbits synchronize, but that means that they follow. But then probably you have also, well, no, you simply say that the distance is bounded. Is that?
No, I say the distance goes to 0. The distance between x and y goes to 0.
And then with you know what is the velocity of this convergence?
Yeah.
Thank you again.
I will not prove it, but this has to do with some kind of. This is actually easy to do. This has to do with a subspectral gap of the Laplacian of the operator that generates the graph. So because, I mean, for this type of problem, there is a close connection to Markov dynamics. So that's why you always hear this words Laplacian. Okay, so now for this, what I'm trying to do now is I'll do this informal. Is try to make this argument here slightly precise. Yeah. So what I told you is that what I want to do, I want to replace the interactions, the hubs, by some kind of local mean fields plus fluctuations. I'll try to do this precise. And the idea is like, again, so I'll take the x goes to 2x. H is very smooth. The number of hubs is small. This is kind of natural assumption, otherwise you're not heterogeneous. The number of friends, so the degree of the hubs is sufficiently large. So in this case, the square root of the system size. Then you can prove the following thing, that for a large set of initial conditions and for exponentially large time in terms of the system size, the hub dynamics can be described by this equation here. where we call this green part that you see reduced dynamics, and we can compute everything that appears there. We can compute kappa, we can compute G in terms of kind of some ergodic properties of the system. And this guy here, for this exponentially long time, is very small. So has very, very small C0. And I want to treat this as noise, by the way. So I wanted to say that I was able to do what I wanted in the beginning. So to say that it was mean plus fluctuations. So what I mean by mean plus fluctuations, like I have some kind of mean field dynamics now going on in terms of this reduced dynamics, plus fluctuations where for exponentially large time, this is actually small. Sometimes I will say during this talk that this is a fluctuation, but this is dynamically generated. Yeah? This is not really a noise. In particular, this is not independent in time and space. Okay, so if you use this kind of, so if you set this, what I call noise to 0, and you analyze the reduced dynamics, then you can explain this type of behavior. So this behavior will be explained in terms of bifurcations of the reduced dynamics. So it's kind of bifurcation analysis now of the mean field system. You can also explain why synchronization happens. So it's basically counting how many periodic points could appear, whether periodic points are attractive or not. So you can explain quite a bit of things. Okay, so let me give you an idea of the proof of this thing. So I have here my phase space. So I will not go through details, it's just really the rough idea. I have here my phase space, and I will call the Bedset. So Lorenzo, this is the definition of the Bedset. The Bedset is where I don't like, where Z is too big. I told you that the Z was small, but the Z can be very big. So it depends on the coupling, depends on lots of things, but okay. Where Z is big is my Bedset. So I call visits to Bedset where I lose control of the Z. So I have a look here where I lose control of the Z. So this would be a set in phase space. And so the key idea here is the following. So inside of the Bedset, I lose control of the system. I don't want to, in any case, I didn't want to look at this Bedset. So what I do, I take my true system, I take my system with the Bedset, and I change the dynamics inside the Bedset. And I do it such a way that outside of this Bedset, where I lose control of all fluctuations, the dynamics is the same. Inside the Bedset, I tweak the dynamics such that the dynamics is still hyperbolic. Okay, so then now what I have to do, I have to study this truncated system. And basically I will consider only two cases where this reduced dynamics is expanded, and the case where the reduced dynamics is hyperbolic, it could have like some kind of periodic points. So the key idea is the following. So here I have my phase space. So here I have some stable directions, some unstable directions, and here's my Bedset. So the key idea was like, if I have a point outside of the Bedset, I can do either the truncated system, the true system, doesn't care, there's no difference. I do one evolution, I hit another point, I do another evolution. Eventually I enter the Bedset. So when I enter the Bedset, I only evolve the truncated system. But you see the idea now, right? The idea is that I turn this problem into a heating time problem. So I will study the truncated system and study the heating time properties now. And the idea, I mean, the key idea was to, if I cook the system in a clever way, maybe the measure of this Bedset is small. Okay, so if the measure of the Bedset is small, then you get all this heating time statistics, and you get this exponentially large time, large deviations. So to succeed when you do this, you have to control the densities of the orbits. I mean, not the densities of the orbit, the densities of the problem. So under some assumptions that I'm not discussing because they're too big, the idea is the following. So if you take the reduced system, and this reduced system has attracting periodic orbits, then you can prove that the truncated system for each periodic orbit, which is attracting from the reduced, you have a ergodic physical measure. So if you project the ergodic physical measure that you get to the unstable manifold or to the unstable direction, then you get a log holder density. And these are the only physical measures that this truncated system has. Again, this is a super special case. This is x goes to x, but at least you could prove everything. And because you get this log holder density estimate, so you can prove that the Bedsets, they have small measure. Actually, the measure of the Bedset would be exponentially small. That's why you get this exponential heating time. Okay, so now I have 5 minutes to discuss a problem. So I will do some kind of inverse problem now. And this will be very applied in particular. Nothing that I said right now about hyperbolicity will apply to this thing here. But I'll use the ideas that I was able to construct. So if you want to discuss about anything now, now is the time, because I'll soon change the system. So more complicated system. Okay, so what I'll do now, I'll take this, what people studied in the 90s, this is called the cat cerebral cortex. So they took the cat, studied the brain. They took all these brains, they have like 63 areas from this cat brain, what they can measure. They know which area is connected to each area. And you measure this data from this area. So the data from these areas, they are not hyperbolic, so they're not x goes into x in any case, but it's slightly more complicated. They have slow, fast dynamics, you see here. So sometimes you have this burst where dynamics is very fast, and sometimes it goes to this quiescent state. But this is a feature of this network. But what's important is that this cat network has this structure here that people call rich clubs. So you have these areas, which in the cats has actually some meaning. For example, the visual cortex, the auditory cortex, right? So you have these blue blobs, and then you have this red blob in the center. So this red blob in the center that you see here, actually they form what people call rich clubs. So they form hubs. They are super well connected, and they form like a club of rich people. So basically, that's the idea of a club of highly connected nodes. What people know is that if you have a synchronization of collective dynamics of this rich club, this is associated usually to pathological states in this cat. So for example, epilepsy. Okay. If you take this data here and you say, okay, I'll take this data. From the data, I want to tell what's the network that generated this data. Is the problem clear? You give me the data, so you give me a time series of 63 nodes. So I have this time series, so this is the membrane potential of these neurons, of these areas. From this data, I want to tell what's the network. And potentially, I want to tell what's the isolated dynamics, and I want to tell what's the coupling function. So I want to tell you.
So say it again, so you give the data, and you want to build a network.
Yes.
But it could be that you have many networks that are generating the same
Actually,
data.
this is totally true. This problem is actually not difficult to prove that this problem is ill-posed. Yeah, but in a certain way, what we believe is that if you don't have some special situation like symmetry groups that generated the network and so on and so forth, then with high probability to succeed. But anyway, let me just tell you, so, because I mean, I tried multiple, not only me, many people tried. For example, if I take this data and do statistical analysis, right, compute some kind of correlation and so on, doesn't work. Then there's some clever people here that do machine learning. I came to them and say, okay, let's do this machine learning. So when I came to São Carlos, this is the first problem I proposed to them, it didn't work. Then we try wavelets and graphs, didn't work. So, okay, so that was a bit of a puzzle. So we say, okay, let's take the time series again. And let's pretend the theorem we just discussed was valid. Because that theorem was like for hyperbolic system, x goes into x, but let's forget about this. Let's pretend the theorem is still valid. So this theorem is saying that this time series actually is being composed by some deterministic part plus some kind of fluctuation. So this deterministic part is chaotic, most likely, at least for neurons is chaotic. And this noise is actually very special because this noise is not noise. The noise, maybe you have some kind of environmental noise, like some kind of thermal fluctuation, but part of the noise is also dynamically generated. And this is the key now for. So what I'm telling you now is that if you have a look at this noise, the noise will be like composed by independent noise, which may come from the K correlations of this hyperbolic dynamics. But it will also have a part of common noise, which has to do with like common connections with this noise. Okay, so now the first result that I want to tell is the following. Let's try to measure this common noise. To measure the common noise, what I'm going to do, I'll introduce something that's called matching index. This matching index basically counts the cardinality of the sets of common neighbors to a node. Okay, so the matching index of node I is the neighbors of I. The matching index, the matching index of I and L is how many friends I and L have in common. Okay, so how many common neighbors you have. And what you can prove, again, for X going to 2X. What you can prove is the following. So if the coupling is not too big, then there is a universal constant where the covariance of the noise can be upper bounded and lower bounded by the matching index.
Tiago, you count intermediate, immediate neighbors or long loops?
Immediate neighbors, not long loops, so just immediate neighbors. But this means like, okay, so this, what I'm telling you now is in a particular case, you can prove it, but we think this is true in general, is that if you take the fluctuation that's generated by this network and analyze the noise, then the noise is actually measuring for you the network structure. The noise is measuring this matching index. So in particular, it means like if you could extract the noise from chaos and analyze the noise, you would recover the network structure. So now there is a procedure here that I will skip. Actually, I'm running late one. I'll skip this procedure. If you run this machinery, you recover the local dynamics. Once you recover the local dynamics, you can filter out the local dynamics from the time series. You're left with the noise. If you're left with the noise, you can do this analysis for the noise. And analyzing the noise, you can recover the network and you can recover everything. So here's the cat cerebral cortex. So here's the real network. So I have the time series for each area. I run this procedure by this dynamical representation and splitting dynamics, chaotic dynamics from noise, and I filter noise from chaos. Once I do it, I reconstruct the network from noise, and this is what I get. So it's quite good. Once you get this, for this particular case, so we are able to reconstruct the triple. I didn't discuss how we do it, but when you filtering noise from chaos, you also learn F. So we learned the graph, we learned F, so you can do some bifurcation analysis now. So that was the starts now new projects, is like whether this procedure is robust. So we tried this procedure many times. We tried for different networks. I cannot prove it, but I'm telling you that under reasonable circumstances, the failure to assign a node to the wrong cluster is only 5%, which is quite nice. We like this very much. And you can also now study, only from the data, you can tell when this network is going to tip to collective behavior, when you're far from the collective behavior. 2 slides and I finish, if I may. So here in the X, I have the coupling alpha. Here in the Y, I have a order parameter. Order parameter here is like statistical mechanics. If order parameter is near 0, then I have total desynchronization. If order parameter is high, near 1, I have synchronization. So nodes, they start behaving. And this is the order parameter of the rich club, of the nodes in red, of the important cluster. So here's the time series that I told you. So again, plotted. This is snapshots. So, and I take this data when alpha is 0.2. I do this reconstruction. So I reconstruct the graph, I reconstruct F, I reconstruct H. Once I have this, I do a bifurcation analysis to see when the system is going to tip. So the prediction is the critical point for tipping this this blob of nodes is 0.4. If we do the experiment, then actually the tipping is around 0.45, but you see already here you have some kind of collective dynamics. Okay, this is a bit too quick. I spent too much time on other stuff. I rushed this part, but I'll be super happy to talk if just drop me a message. We have some further applications now to lasers, so this is a successful project. So if you take data from lasers, you can do the same thing. You can recover the network and analyze this type of stuff. I discussed some problems when we could solve stuff. Basically, we could only solve stuff for very trivial cases like x goes to 2x and perturbations of this. All the big problems, they're still open, so this is very, very annoying. And one problem is like I have this huge network. One problem like maybe you guys can have. So I have this huge network and I want to do this mean field argument. But I take one node out of the periphery and I put it as rotation. Then this argument that I construct does not work. So this is very, very annoying. Although you see, kind of, I should be able to throw this node away. I also don't know how to do this for flows. And to be honest, I don't know how to do this for local honors of dynamics. But if you ignore what we don't know, and actually there's kind of surprising stuff like you take data and you can only process data because you know the dynamical system. So this is actually very strange. In any case, dynamical system is essential and ergodic theory is essential to solve this problem. So thank you very much.
Well, let's thanks Tiago. Are there any questions, comments?
So one question, in the case of predicting data, you were assuming that in each node, the dynamic that you are taking in consideration is an expanding map, and then it was all about finding the couplings.
Yeah. So there are two steps, and maybe I was not clear. So if the dynamics was an expanding map, then you could prove that the time series would be chaos plus noise. In the neurons, they're not expanding. In particular, they're kind of there's low fast dynamics. It's more complicated. But I did the assumption that although they are not hyperbolic, the theorem or some kind of the same resulting spirit will be valid. If you assume the resulting spirit will be valid, then this means like in each data now, I have a superposition of a dynamical system which is isolated plus coupling and plus noise. So what I did some kind of tricks to extract what's the local rule. You can do this by Takens reconstruction. So once you learn the local rule, you say this local rule now is local dynamics plus coupling. But because the local rules, they're not the same for everyone, you can learn what's the coupling. That's the idea. So you say
so first you have to identify which is the local rule, and then is the coupling.
Yeah. I say the following, that so how you say, what's my definition, or how do I find it?
No, how do you find it? So do you have to find first the local rules? So each dynamic in each node,
yeah,
and then how they are going to.
Yeah, so I say, yeah, precisely. Thank you very much. So I say, so if I do Takens reconstruction, I find F1, F2, F3, F63. Now I say there is a function that if I subtract a multiple of this function from this many Fs, then all these functions become the same. So they become all linearly dependent.
Okay.
So this is what I do. And I say the multiple of this function is the coupling.
Mm-hmm. Okay, thank you.
There is another question.
So Tiago, you made the assumption that the conclusion that you want to take in this problem was more or less similar to the conclusion that you got in the previous theorem that you explained. Mm-hmm. And in some slides you mentioned that the result you got was like comparing to some reality was like 5% correct. But so it says that the assumption is more or less correct, though. If I understand.
Yeah, this is a pain. Is that I can only prove such a limited case, but probably this result is true in more, because there are a few tricks. You see, I'm not claiming that this result's true forever. Actually, I have a counterexample, so this result will not be true forever. Sometimes like the result stays like this, and then you go to fixed points, but I'm only interested in finite time. So I guess if we knew how to do finite time dynamics, so probably most of the complications of dynamics would not appear. And then you don't really care much about it. But to be honest, I don't know how to do it. Yeah. So I was discussing this with Sebastian, for example. If you take quadratic family, this result is not true because it's too complicated. But for finite time, you see all this complication of quadratic family does not appear. So in particular, if I code the quadratic family in the computer, it behaves precisely like I wished. So there is a gap, which is very annoying. How to go from asymptotic to finite time and stop in a good way.
I see, thank you.
I have a quick question. Probably I missed it, but what do you mean for largest set of initial condition?
Yeah.
How large is it?
Large with respect to the Lebesgue measure.
Okay.
So the sets, the measure of the set where this result is valid, the measure goes to 1 when the network goes to infinity, the network size.
Okay, thank you. Is there any question?
In the applied problem at the end, I was with a little doubt because you mentioned that the number of nodes, you have an idea of what it is, and you want just to recover the connections between those nodes, or you don't know even the number of nodes.
So we started this problem. So somehow my computer froze. Now it's back. Okay, so the idea was the following. So you give me the time series, and I want to tell what's the network that generated. So the first step I told you is like if you take this network and write the time series as being deterministic plus fluctuation, you can take out the deterministic part, so left the fluctuation. Now you do some kind of a mutual information analysis of these fluctuations. Then what I proved is that these guys actually measure some network property, what is called match index. So this means like you can find clusters just from like correlation analysis from these nodes. Then I can identify all clusters, and I'm telling you that this analysis is very robust. You never miss a cluster. And then there's an next step if you want to correct further. So inside each cluster, how you connect it actually, you should do something else. But usually this is not so important.
I see, thank you.
So there are no more questions. Let's thank Tiago again.